Assalamualaikum. In the last lecture, we learned that synchronous motors are not self-starting. Why? Because this stator magnetic field rotates with very high frequency, and due to inertia of the rotor, this rotor cannot quickly gain speed to catch up this stator magnetic field. Therefore, it fails to rotate. Rather, with each pass of this stator magnetic field, the direction of induced torque is reversed, and that causes high vibrations in the rotor, and that can damage the synchronous motor. So what are possible solutions to make the motors self-starting? We have talked about two solutions in the last lecture, and in today's lecture we shall talk about the third solution, that is the damper windings. This is the most popular solution, and due to its low cost, it is very frequently utilized in synchronous motors to make them self-start. So what are damper windings? These damper windings are straight bars which are placed in the rotor like this one. These are bars which are placed like this one, and furthermore these bars are sharded at both the ends, that is at the front end as well as at the back end. So these are sharded with the help of sharding rings. Initially, what they do is they disconnect the field circuit, and only these damper windings are effective, and these damper windings help the rotor to get speed, and once this rotor gets near synchronous speed, then this field circuit is again connected, and then rotor starts rotating with synchronous speed. So how do these windings help the rotor to start? Let's elaborate this point. So we have this rotor. We have this rotor of this synchronous motor. Since field windings are disconnected, there is no magnetic field due to field windings. So VR is not there. There is only one magnetic field, stator magnetic field, which is rotating. So let's see the situation at time instant omega t equal to 0 seconds. At this time instant, here is the stator magnetic field, ds, which is rotating in this direction. And this rotating magnetic field links with these conductors, and we know that when a conductor is placed in a magnetic field and there is relative motion between the magnetic field and conductor, voltage is induced in those conductors. What is relation for the induced voltage? Magnetic field and conductor. Magnetic field links with these conductors, and we know that when a conductor is placed in a magnetic field and there is relative motion between the magnetic field and conductor, voltage is induced in those conductors. What is relation for the induced voltage? We know that E induced is equal to V cross V dot L, where V is the flux density vector and V is the velocity of conductor relative to the magnetic field. Here, these conductors are stationary and magnetic field is rotating. So what is the direction of linear velocity of this magnetic field? It is angular velocity is in this direction, so linear velocity of rotation of this flux density vector is this one. And flux density vector is in this direction. This is V, and this is velocity of the stator magnetic field. However, in this expression, V is velocity of the conductor relative to the magnetic field. So velocity of conductor relative to the magnetic field is opposite. to the velocity of magnetic field relative to the conductors. So this is velocity of the conductors. So V cross B, this is V cross B, that is out of the surface of board. So voltage will be induced in these conductors, which will cause the currents to flow in this direction in these conductors out of the surface of board. What about these conductors? For these conductors, the polarity of the voltage is such that current will flow in this direction. So now current is flowing in these damper windings, and current carrying conductors have their magnetic field. What will be the flux density vector due to current in these damper windings? Current is entering from here in the windings, and then through the starting ring at the back end, it enters into conductors and leaves from here. So this is the direction of current in these damper windings. Into the board at the back end there is starting ring, and through the starting ring current enters into these bars, and then here it leaves. So there is a magnetic field due to damper windings, and the direction of that flux density vector is towards right. And now there are two magnetic fields, and we know that due to interaction of these two magnetic fields, a torque will be induced. We have derived this relation, K Br cross Bs. In this case, instead of Br, we have Bw. So this is B. Instead of Br, we have Bw. So this is Bw cross Bs. That is due to interaction of these two magnetic fields, a torque will be induced, and the induced torque is in counterclockwise direction. So this corresponds to time instant omega t equal to 0 seconds. Next, to analyze another time instant, that is this situation. So at omega t equal to 90 degrees, the stator magnetic field will have rotated by 90 degrees. This is Bs, corresponding to omega t equal to 90 degrees, and that corresponds to time. If, for example, we have supplied the voltage signal with a frequency of 60 Hz, then corresponding to this thing, we have time equal to 1/240 seconds, because this Bs completes 60 revolutions in 1 second. That is, for one revolution, it takes 1/60 seconds. One revolution, 1/60 seconds. And here it has rotated by quarter revolution, so 1/4 revolution, that means 1/240 seconds. So at this time instant, Bs is over here. And how much voltage will be induced in these conductors? Corresponding to this time instant, no voltage will be induced in these conductors. Why? Because no flux is passing through these conductors. So at this time instant, induced torque is equal to 0. Since no current in these conductors, mean dW, the magnetic field due to current in these windings, that is 0, and hence induced torque is also equal to 0. Next, analyze the situation corresponding to omega t equal to 180 degrees. Although at this time instant, induced torque was non-zero, it was in counterclockwise direction. However, rotor is still at this same position because of its inertia. It cannot quickly move. So in this brief time, it would have hardly moved to any significant angular displacement. So we have still taken the same angular displacement of this rotor. And now this Bs, that has rotated by another 90 degrees, and that corresponds to omega t equal to 180 degrees, and that corresponds to time s downwards, and of the status relative to this conductor. If this conductor, current will start flowing in these conductors. Direction of current from and leaving through these conductors through the shorting rings. So the flux density vector due to current in these conductors, that is towards right, BW. So again, there are two magnetic fields, BW and BS, and what will be the induced torque? Induced torque is BW cross BS. That is non-zero, and again in counterclockwise direction. Furthermore, you can analyze the situation corresponding to omega t equal to 100.
Torque is a measurement of the force which causes something to rotate around a point. Think of a wrench and a nut which has seized up. Using a small wrench is very hard to free the nut. Using a long wrench will make it much easier. That's because of torque. If we used a 30 centimeter wrench and applied 90 newtons of force, we have 0.3 meters multiplied by 90 newtons, which gives us 27 newton meters of torque. However, if we applied the same 90 newtons of force to a wrench that was 60 centimeters long, then we would get 0.6 meters multiplied by 90 newtons, which gives us 54 newton meters. So from this simple formula, you can see we have more force acting on the nut by using a longer wrench. Essentially, we're using a larger circle to turn a smaller circle. By changing the size, we change the speed and the torque. A low gear provides low speed but high torque. A high gear gives high speed but low torque. If you have ever ridden a bike, you'll know it's very difficult to start pedaling in a high gear. So we need to start in a low gear to get the bike moving. At a certain point, our legs are spinning very fast, but we can't go any faster. So we need to change to another, higher gear. Once we reach a steep hill, we need to move to a lower gear. The same with a car. We start in our lowest gear number and work our way up as the vehicle increases in speed. Then we change down as we drive up a hill. Okay, that's it for this video, but to continue learning,
open it. We must look at it as a rotating object, which is rotating about a fixed axis hinged at one of its sides. For entering a room, we first have to rotate the doorknob, and then you either push the door or pull it depending on the type of the hinge. If you remember what we learnt in kinematics, the word push or pull represents force. We are applying the force on the handle of the door in order to rotate the door, but in this case, the force alone is not responsible for this rotation. There is something else in action here. It is the distance from the axis to the point at which we apply the force. This combination is known as torque. As push or pull denotes force, twisting creates torque, which is rotational equivalent of force. Torque causes rotational motion of that object about one or more axes that pass through its center of mass. It is denoted by the Greek symbol tau. Mathematically, torque about a point is defined as the vector product of position vector and the force. Torque is a vector which is perpendicular to both the position vector and the force vector. As a result, the torque of a vector perpendicular to the plane defined by position vector and force. The direction of torque is given by the right-hand thumb rule. To apply the right-hand rule, put the fingers of right hand along the position vector and L. Magnitude 2000 cos frictional force equal to N cos 30 degree.
270 degrees. That situation is over here. So stator magnetic field is at this location at omega t equal to 270 degrees, and therefore no voltage will be induced in these conductors. No voltage induced in these conductors means there will be no magnetic field due to these conductors. There is only one magnetic field, and hence induced torque will be equal to 0. So what we observe, and this cycle will keep rotating, that is again it will be counterclockwise direction, 0, again counterclockwise direction, and non-zero. So what we observe is that although the magnitude of the induced torque is fluctuating, it is changing, however its direction is always the same. It is always in counterclockwise direction. So this is opposite to the situation when we had field windings. In the case of field windings, the direction of induced torque that was changed during each pass of the flux density vector Bs. However, with the damper windings, it is always in the same direction, and that will cause the rotor to rotate in counterclockwise direction. These conductors means there will be no magnetic field due to these conductors. There is only one magnetic field, and hence induced torque will be equal to 0. So what we observe, and this cycle will keep rotating, that is again it will be counterclockwise direction, 0, again counterclockwise direction, and non-zero. So what we observe is that although the magnitude of the induced torque is fluctuating, it is changing. However, its direction is always the same. It is always in counterclockwise direction. So this is opposite to the situation when we had field windings. In the case of field windings, the direction of induced torque that was changed during each pass of the flux density vector Bs. However, with the damper windings, it is always in the same direction, and that will cause the rotor to rotate in counterclockwise direction, and the rotor will gain its speed. So with only damper windings, if we only have damper windings on the rotor, this rotor can achieve near synchronous speed. However, it can never rotate with synchronous speed. Why it cannot rotate with synchronous speed? For example, if this starts rotating with synchronous speed, then this conductor, what will be relative velocity between Bs and the conductor? Bs is also rotating, this conductor is also rotating. There will be no relative motion between this Bs and these conductors. No relative motion means no voltage will be induced. No voltage induced means no current, and hence no dW, and induced torque will be zero, and that will cause the rotor to slow down. So with the damper windings, rotor can get speed to near a synchronous speed. However, it can never achieve the synchronous speed. So once this rotor gains near synchronous speed, we can again connect the field windings, and then this motor will start rotating with synchronous speed due to the phenomena which we studied for the case of synchronous motors. So damper windings not only help the synchronous motor to make it self-start, but these windings here is the stator magnet. V cross V, and magnetic field is rotating. V is the flux density vector, and V is the velocity of conductor relative to the magnetic field. Here, these conductors are stationary and magnetic field is rotating. So what is the direction of linear velocity of this magnetic field? It is angular velocity is in this direction, so linear velocity is in this direction. This is in this expression, V is velocity of the conductor relative to the magnetic field. So velocity of conductor relative to the magnetic field is opposite to the velocity of magnetic field relative to the conductors. So this is velocity of the conductors. So V cross V, this is V cross.